And now for the final case. In all the previous cases, the ground level was set artificially low to remove its influence on the transients in the pipeline. This case brings a realistic ground profile back into play. We are returning to the familiar DN100 mm stiff pipe and pump power failure at 7 litres a second flow rate. This time the hydraulic grade line looks like this, in relation to a ground profile that rises realistically from the pump station on the right to the destination tank on the left. Closing here out of this mode and going over and running the transient simulation. Now this looks a lot different than our previous examples, where the ground profile had no influence. Do you remember what the light blue blocks mean up here? They mean that at some time during the simulation their water element vaporizes. And it is vapor at time steps when the block is shown as white. Just watch the animation for a while, and then I will explain what is happening. I will rewind the animation, start it from the beginning, and stop it about here and go back to the 3 seconds time step. Here at 3 seconds after the pump has lost power, the wave front, the head drop, has travelled down the pipe. The pressure in the more elevated parts of the pipeline has dropped to vapour pressure. The water in these parts of the pipeline is now vapour, not liquid. The water column has broken. There is liquid water still travelling into the tank. Liquid water is still in the upstream half of the pipeline, and a big vapour pocket is in between these two liquid sections. Now stepping forward to the 4 second mark, the wavefront has reached the tank and reflected as an increase in head. As this wavefront comes back from the tank, it increases head in successive parts of the pipeline above vapour pressure. The water at these points changes from vapour back into the liquid phase. These little spikes, wavefronts, radiating away from the points where the vapour is recombining with the adjacent water column, are created by the way the software models vapour pockets. I will come back to this subject and talk about it more in a later lesson. For now, it is sufficient to understand these little spikes as being unreal. Now, letting the simulation continue to run, we can now see that separating the water column with vapour pockets, which later collapse and recombine into a single water column, totally changes the transient behaviour of the system. The dynamics of the water column is changed dramatically. It is important to understand that vapour head of water at normal ambient temperature is about -10 meters. In simple terms, this means that the pressure outside the pipe is greater than pressure inside the pipe. If the pipe is buried with leaky joints, contaminated groundwater could be sucked into the pipe. If this pipe is cross-connected to other water systems, for example an untreated raw water module in a water treatment plant, without adequate backflow protection, water of an unacceptable quality can be sucked back into the pipeline. Interaction with the ground profile has the potential to change the water dynamics and the water quality risks